So that should be.
Well, it's also
But that's saying that they double charged you.
All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Good.
Good. Midterm project's done, so that's out of the way, so that's good. So I haven't started looking at them yet, and so I I'm hoping to grade them before the end of the week, and so you should know your score based on that. Okay. And so one of the goals of having a midterm project like this was to kind of give you a little bit of a practice run, because your final project is going to be very similar to this. And so for your final project, I'm going to ask you to kind of do a full finite element analysis, just like the midterm project. I'm going to have you write a report to kind of explain everything. But the final project will have some additional components, of course. But I wanted to give you a chance to kind of early on to get some practice, writing a full report like that, because the final project is going to be a month. So I know the midterm project was quite a bit of work, but hopefully this makes the final project a little bit easier for you. Okay. All right, and so in terms of this week in class, we have another ANSYS week. And so, just like we did for, the last two answers activities, today I'm going to be talking about some of the theory that goes behind the feature that we're going to look at on Wednesday. And then Wednesday, we're actually going to put it in practice. Okay. And so this week's going to be really, hopefully exciting. And so, I think this is actually one of the coolest things that you can do in ANSYS. And it's something that I've presented on in the past. And so, there's a few, I know there's a few people in the class who've taken my previous finite elements courses. And so, we did optimization back then. But, if I could be, to be honest with myself, the past optimization activity that I had kind of sucked ass. And so I was really hoping to kind of really dive deeper into it this year and really make something that's actually more useful. Because, I think the optimization activity I did before, it was kind of cool, kind of what it did. But the kind of the way that I presented it was just not that useful to people. And so, I really kind of, reformed that whole thing, kind of built this whole week up from scratch. And so, hopefully the way that this is presented now is a lot more useful. And, something that you can actually take into into industry and beyond. And so, but because of that, we'll be taking a little bit of a deeper dive than before. And so we're going to be diving a lot more into optimization theory. Although not really, but just talking about how we define certain things. But hopefully this is going to be a lot more useful to you. Right? And I think this is kind of the first time where we're actually doing something in line with the title of the class. And so, we've been learning ANSYS this whole time, but we haven't really talked about how we can actually use it for actual design. And so, we'll be talking today about how we can use optimization to actually, design stuff or have ANSYS design stuff for you in the computer. Okay. All right, and so I think that's everything. And so, are there any questions I can answer before we get started? Oh, remember, activity 5 is still out there, and so remember the car crash activity. I think that's due tomorrow night by 11:59, and so make sure you get that in. Okay. Was there a question over there? Okay. All right. So let's go ahead and get started. All right. And so the theme of this week is something called optimization. Okay. All right. And so let me just kind of first start off by saying that, one of the really nice features of ANSYS and finite elements in general is that you can digitally, run a test, without having to produce any physical prototype, right? And so this is something that we already know. Okay. Right. And so you can take a geometry and you can find out, if you subject this geometry to certain loads, to certain constraints, you can find out, what's the deformation going to be like? What is it going to break on me? What's the stresses are going to be like? Okay. And you can do this, relatively really quickly, right? And so if you compare the amount of time it takes to set up an ANSYS simulation versus the amount of time it takes to set up a real life physical test, it's way faster to do the ANSYS one. Okay. And because this is way faster, ANSYS is great for this technique called iterative design. Okay. And so the idea with iterative design is that, say that you're in charge of designing a certain part for your engineering work. Okay. With iterative design, what you can do is you can design the part, maybe not be super careful about how you dimension everything. You can run the simulation, you can check the results, and then based on the results, you can go back and change the design really quickly, right? And so you kind of make all these little incremental design changes until you reach, what you deem to be an optimal design. Okay. And so that's very different from, how you would design something with physical tests, right? Because if you were designing something and checking stuff with physical tests, there's a very limited amount of times that you can try your design, right? And so, kind of before the world of FEA, the way that design was done was that, an engineer proposed a design and they kind of designed it the best they could with hand calculations. They try to verify that with a single physical test, okay? And then based on that, he would go and make modifications, and maybe he would be able to produce one or two more prototypes. But the prototypes are really expensive, right? And so this is only so much you can do. But with FEA, you can kind of do this as many times as you want, and so the only limitation there is really time, and not really money. Okay. And so if I could summarize the whole design process into a flow chart, it would be something something like this, right? And so let's say that you start with some kind of initial design. Okay. Then from this design, you can conduct a test. Okay. And this is where your FEA comes into play, right? And so you would conduct the test digitally with FEA, okay? Okay. And then based on the results of the simulation, you would evaluate your design's performance, right? And so you would check to see what the what the maximum deformation was, what the maximum stress was. Okay. All right, question. So is optimization similar to smart design feature in ANSYS? I actually haven't tried out the smart design feature in ANSYS, so I don't want to comment on it. But it might be kind of similar, but I'd have to look into it before I give you a full answer to that. Okay. All right. Okay. And so from here you check. Okay. And so because it's a check, I'll put a diamond block there. Okay. And so you can check to see, if the performance is that something that you're satisfied with, and so are you happy with the performance that you have? Okay. If the answer is no, okay. And so if you think that you can do better, then you can enter this block here where you improve the design, okay? And so maybe you change some of the design parameters, you change the material, you change the thickness, you change some of the dimensions on your CAD model, okay? And then you enter the loop again, okay? And so, after you improve the design, you would conduct a test, you would evaluate the performance, check and see if you're satisfied, and so on and so forth, okay? Eventually, you will be satisfied with the design and you kind of kick yourself out of this loop, but then until then, you keep going through this, okay? And so this loop in here, this is going to be the subject of today's of this week's activities, okay? And so I've already had you guys do some practice, with this already. Right? As you think back to activity three, I had you redesign the signpost. And so I had you either make it thicker or you change the geometry or change the material of the signpost, to improve the design, right? And so it's very possible to do this, manually, okay? And so if you perform this manually, that would be essentially the same as activity three, okay? Right. But ANSYS actually has tools for you to do this entire block automatically. Okay. And so we're going to talk today about how do we automate this entire process. And so that you have, instead of you kind of sitting there changing a parameter, running a simulation and see what happens and kind of doing all this and kind of sitting at your computer kind of wasting your time, you can have the computer do all this for you. And that's not to say that it'll be fast. And so optimization is a little bit of an expensive task, but at least you can do something else while the optimization is running. And so you can go ahead and make yourself dinner, you can go to the bathroom, you can watch maybe the Netflix show that you've been putting off, right? And so, optimization is a really nice feature to kind of automate this design process and then automatically come up with an optimal design. Okay. All right. Any questions on this so far? Okay. All right. So let's talk about what optimization is and how do we set it up. Okay. All right. And so optimization is a great tool, and if you but if you kind of read the literature into optimization, it actually has its roots in applied mathematics. Okay. Okay. And at its core, and so if you take like a class in optimization, and actually I think we have one in this department, although I don't know the last time it was taught. At its core, optimization, what it seeks to do is it tries to find the minimum or maximum value of a mathematical function. Okay. Okay. And so let's say that, if we just do a 1D example, right? And so let's say on the x-axis, we have the, an x variable. And on the y-axis, we have f of x, right? And so let's say that f of x is a function, that maybe looks something like this, okay? Right. And so if we ran an optimization procedure on this function right here, we would say that this location here is the optimal value, okay? Right, and so we say that that's f opt, and so that's the optimal value of the function, and the location where that occurs is x opt, okay? And so the optimization procedure will find both of these for you, okay? Right. And so for a 1D case, it's really simple to do because we can just look at the function and say, obviously this is the highest point, right? But this gets a lot more complicated when you start to have 2D functions, 3D functions, 4D functions, 5D functions, right? Okay. Because once so 2D, you can kind of still kind of visually look at and see, what's the peak. But once you get into 3D, 4D, 5D functions, they don't have a visual representation that really kind of makes sense. And so, those are the cases where the optimization procedure really helps you out. Okay. And so a lot of design problems that you're going to be tackling in engineering, they're going to be within that space, right? And so most of the time, when you're performing optimization, you're going to be designing over several design variables. And so it's not just going to be one or two, it's going to be 3, 4, 5, or 6, or even more than that, okay? And so that's why optimization kind of has its place in engineering, because just naturally, just by the work that we do, we're optimizing over so many different variables, okay? Another way that that optimization is useful is that it works in cases when you don't even know the mathematical form for f as well. Okay. And so here, I've drawn it visually, which kind of implies that we know what it looks like, but we don't even need this. Okay? Okay. And so we don't even know what the function looks like most of the times, right? And so how do you find the optimal of a function that you don't even know? Right? And so that's exactly what the optimization procedure, aims to do. Okay. And so on the next page, I'll show you kind of an example of, how you would set up an engineering problem as an optimization one. And then, we'll dive deeper into how to actually set this up in ANSYS too. Okay. But that's the basics of optimization. And so basically all you need to know about optimization is that you set up some kind of, function. It doesn't have to have a mathematical form, but optimization will try to find the optimum or the maximum or the minimum of that function. Okay. All right. Any questions on this? Okay. All right. So what's an example of what this looks like in engineering? Okay. And so let's say that we're in charge of designing, we're in charge of the design of a curved pipe. Okay. And so let's say that this pipe, makes a curve just like this. Okay. Pretend that I'm not terrible at drawing and that the diameter is consistent. Okay. All right. And so we have the diameter of the pipe here. And we also have the radius of curvature R. Okay. All right. And so when you're designing this pipe, those are variables that you have control over. Okay. Because depending on the value of the diameter and the radius, that tells us of what pipe that we might order from McMaster Carr, or how much we have to bend it, or how we machine this whole process. Okay, and so those are basically, you can consider those as our design variables. Okay. Another term that you'll see for these is these are our input variables. Right. And so your design variables are the variables that you can control over as part of your design that have a direct influence on the response. Okay. Okay. All right, and so if you want to connect this example to the graph that we shown on the previous page, this D and this R, those would be the same things as like the X variable from our function. Okay. Okay. Right, and so usually our goal would be, if we were going to simulate this curved pipe in ANSYS, we would tinker with the values of D and the values of R, and we'd run simulations on them, until we got a simulation result that we're happy with. Okay. And so, we would consider D and R here to be our design variables. Okay. And so for this, example, I've chosen 2 geometrical parameters as our design variables, right? But your design variables can be even more beyond this too. And so it can be even like the material that you choose. It could be, the overall, something overall about the geometry too. So maybe like an overall, bounding box for the geometry. Okay. So basically any aspect of the design that you can control, that you can modify, you can have that be a design variable for your optimization. Okay. And as you can imagine, for a simple case like this, there's only so many variables that you choose, but for any kind of complex CAD, there's dozens and dozens, almost limitless amount of variables that you can choose as your design. Okay. Because if you think about, a typical CAD model, the amount of dimensions and the amount of parts in a complex CAD model can be really, really high, right? And so in theory, you can choose all of those things to be design variables, and so you can have ANSYS, fiddle with almost everything in your geometry. Okay. But you don't want to do that, and so you want to choose your design variables carefully. Okay, and so we'll talk about that on the next page. Okay. All right. Any questions on this? Okay. And so we can have ANSYS modify lots of aspects of our design. But we have a big but here, right? And so it's the caveat that kind of prevents us from doing a lot of things in this class, and that's computational cost, right? And so as with anything that we have in this class, so the more things that you consider, or the more like we usually do, like the more elements that you have, right? The more design variables that you have, the more expensive the optimization is going to be. Okay. And the thing with optimization is that, I think, everyone in this class, we've all kind of experienced, what happens when you pump up the number of elements in your analysis, right? So you pump up the number of elements and the cost kind of goes up just like that, right? And so with optimization, that scaling goes even harder. And so, this scaling is super, super hard. And so I'd say it's even an exponential scaling, right? And so you have to be really careful. And so even just going from like 2 design variables to 3, that actually increases the cost by a really significant amount. Okay. And so you have to be really careful for which aspects of your geometry that you choose as design variables. Okay. Okay. And so what's a good number? And so I would say if you're in the ballpark of like 1 variable, 2 variables, 3 and 4, I'd say you're going to be okay for most of the time. Okay. Right. Anything beyond this, and you're kind of asking for trouble. Okay. And so, but if you have a lot of time, and so if your design isn't going to be due for a month, and you can just run an optimization on that entire time, then go for it. And so if time is not a factor, by all means, run the optimization as long as you want. But if you want your optimization to finish more quickly, try to limit the amount of design variables. Okay. Because otherwise, you're going to be sitting at your computer for a long time. And even for the activity that we're going to do on Wednesday, there's going to be a lot of time that we're just going to be kind of sitting in front of the computer, kind of just waiting for it to finish. And so, it's even more expensive than unsteady simulation. And so, just kind of be prepared for that. Okay. All right. And so that's design variables. Okay? And so my advice with the design variables is to think about, what are the aspects of your design that should have the most dramatic influence on the outputs. Okay. Right. And so whatever design variables have that big influence, those are the ones you want to pick for your optimization. For the ones that don't really have that big an influence, maybe it's maybe it's the I don't know, maybe it's the location of like a drill hole or something like that. Then maybe leave that off, because something like that's just going to add a bunch of cost to your optimization, without really adding anything substantial. Okay. All right, and so that's the inputs to an optimization. And so that's kind of the first part. And so the first part of an optimization is you need to decide, what aspects of the design do I want to tinker with, that I really want ANSYS to find and optimize for me. Okay. And so then the other part of an optimization is to define what's known as your outputs. Okay. And so an output of an optimization is some kind of computed quantity whose value is influenced by the inputs. Okay. And so some common examples for an output in finite elements would be things like the maximum deformation. Maximum stress. Even things like the overall mass or the overall volume of the piece. All of these are considered outputs. Okay, because a lot of times, when you run a simulation or when you run a design, you want to minimize a lot of these things, and so you want to minimize the deformation, you want to minimize the stress, you want to minimize the volume or the mass. Okay. And the values of these are going to be influenced by your input parameters, right? And so depending on what the geometry of your part is like, what material that you choose, how much of that material, and so that's going to influence these results, okay? And so the other part of the optimization is to define for ANSYS, what aspects of the outputs are you interested in optimizing, okay? All right. Any questions on this? Okay. All right, and so those are the kind of the two those are the two kind of aspects of an optimization procedure. And so you need to define the inputs of the optimization, and you need to define the outputs. Okay. And so with that in mind, we can have kind of a more kind of specialized definition for an optimization with regards to engineering design, okay? And so what we can say is that optimization finds to seek the values of the input parameters that either maximize or minimize the outputs of a finite element simulation. And whether you choose to maximize or minimize, depends on what you want to do. Okay. All right, and so visually, it's let me draw a flow chart first, and then we'll go over an example of how this would be set up in ANSYS. Okay. All right, so the first thing you would need is your list of inputs. Okay, and so your inputs would be maybe something like x1, x2, x3, yada yada yada. Okay. And so, each of those X values would represent, maybe certain geometrical dimensions in your model, or they might represent certain material properties, okay? And so with those inputs, you would then evaluate the outputs. Okay, and so this would be like F of X1, X2, X3, yada, 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 okay? Okay, and so this step right here, this would be actually running the finite element simulation. Okay. And then from there, you would, based on this results, is you would basically check your results. And then based on those results, you would then update your inputs. Okay. And then kind of run this whole thing again. Okay. And so in the end, when you ask ANSYS to run an optimization procedure, you're actually asking ANSYS to run dozens and dozens of simulations, and sometimes even hundreds and hundreds. Okay. Okay. Right, and so an optimization is not something that you can do, lightly. And so it's even for a modest problem, it can still take a while to run. And so you want to be careful when you run an optimization. Okay, but it is a very valuable tool because it ends up saving you a lot of what I call like keyboard time. And so, it might take, the amount of clock time that it takes is long, but you don't have to be there the whole time. You can just go ahead and do something else. As an example, I'm still kind of developing the activity for Wednesday, but I hit go on ANSYS, and then I went out to lunch, and then I came back, and then it was done, right? And so that was an hour of time that I was working, right? Because I was working on the optimization, but I didn't have to be there, right? I was eating a sandwich at which instead. All right, any questions before we go into an example of how we can set this up in ANSYS, or how what the logic is? Okay, all right, so let's talk about a very simple example that you can do in ANSYS. And so we're not going to be doing this on Wednesday, so we're going to do a little bit of a more interesting case, but I think this one is very kind of easy to grasp. And it has my favorite example, the one that we've used a ton in this class, and it's a cantilever beam. All right, and so let's say that we have a beam like this, okay? The length of the beam is given by L, okay? And then at the end of the beam, we have a load P, okay? We also have the dimensions for the beam cross section. And so let's assume that we have a rectangular beam, okay? And then where the width of the beam is given by W and the height of the beam is given by H, okay? And so, let's say that we're in charge of designing this beam, right? And so when we're designing this beam, we're in charge of determining what each of these variables should be, right? And so we have, the length of the beam, we have the width of the beam, we have the height of the beam, right? And so we'll say this is design variable 1, this is design variable 2, and this is design variable 3, right? So all three of these things have to be determined, right? And we're going to determine them through an optimization procedure, okay? Okay. Right, and so that's what we want to optimize. Okay? And so those are the inputs to our optimization, right? So those are the design variables, because those are the things that we have direct control over in our design. Okay. Yeah.
I have a question.
Sure.
So let's just say if we're designing something like this in real life, wouldn't those, let's say if we're building a building or something, wouldn't most of those be set already by the codes or standards that we came up with?
Mhm.
And then in that case, can we tell ANSYS, okay, test out different materials that we give it?
Yeah.
Or test out other variables other than just the dimensions of our model?
Sure. Yeah. Basically, anything that you have control over in ANSYS, you can have ANSYS optimize over. And so it would be a little bit different for materials, because for these ones, these are, I call them kind of analog variables, because they can take almost any value in a range. For materials, you would have to give it an explicit list of, here are the materials that I can use. And so you can have them optimize over that too. But even in cases where you're kind of limited by, by codes and stuff like that, there is still some freedom in how you design stuff too. And so maybe you don't have you don't have a ton of freedom, but there's still some, within this range, I can choose a thickness in this range, and that's what you can use this for too. Yeah. Mm-hmm. Yeah, optimization, you can do that too. And so instead of giving, right now the way I'm describing this, I'm saying that ANSYS has free range, but in reality, most of the time you're going to constrain the variables that only look within this range. So here's the lower bound, here's the upper bound. Yeah. Mm-hmm. All right, and so let's say that we want to optimize these values to minimize two things, okay? And so first of all, let's say that we want to minimize the structural stresses, okay? And so let's say that we want to minimize the equivalent stress. Okay. Right, and so that's pretty standard, right? And so we don't want our beam to break. And in fact, we want to minimize the risk of it breaking. And so we want to come up with a design that minimizes this equivalent stress. Okay. And we also want to minimize the cost of production too, right? And so we want to produce a beam, that's not only safe, but also, it's not going to cost us an arm and a leg to produce, okay? And so the way that we can evaluate cost of production is by just simply computing the volume. Right? Okay. And so we're going to seek a design that's also minimal in volume, as well as in stress, okay? Because the less volume this beam has, the less material that we have to use to build it. And then, the less cost that we're going to incur in the end, okay? Right. And so, with all these things combined, these two things would be our outputs. Use a different color for that. Okay. Right. And so these would be our outputs. And so with these, with these defined like this, we can then tell ANSYS to kind of go for it. And then it'll find optimal values of these that find the minimum of these functions. Okay. All right. Any questions on this? Okay. All right. And so, just like we kind of just discussed now. So one thing that's useful, and ANSYS actually forces you to do this, which is nice, is that you can place upper bounds and lower bounds for your design variables. Okay. Right. And so you can basically tell ANSYS, don't bother looking in certain places because that's just not going to be feasible for our design. Okay. And so one example of a really cheeky solution to this problem, right? And so if I gave maybe like a freshman engineering student, so give me a beam that minimizes all these things, right? Minimizes the stress and minimizes the cost of production. He might giggle and say that, why don't we just set L is equal to 0, right? And so we just have no beam, right? So if we have no beam, it's going to be free because we don't have to make any beam. And if we have no beam, then there's no stress, right? So problem solved. But obviously we can't do that, right? So we have to have some kind of beam. And so let's say that we have a constraint where we have to have actually at least some length, because we actually need to support this load P right here, right? And so that's what the upper bounds and lower bounds can do, right? Okay. Another example of how you can use upper and lower bounds is to make sure that maybe the geometry of your part has to fit within a certain range. Okay. And so that might be a case where you put the upper bound, okay? And so ANSYS will kind of force you to do this, which is good because it is good to do. And actually the default in ANSYS, is to set the lower bound to be 90% of the whatever starting value it is, okay? And the upper bound is 110% of starting value. Okay. And so, for example, let's say that our initial design for this beam, and so the first design for the beam that you come up with in ANSYS, let's say that beam is 20 meters long. Okay. Okay. And so if your initial design length is 20 meters, that means ANSYS will set the lower bound to be 18 meters. Okay. Meanwhile, the upper bound will be 22 meters. Okay. Right, and so that's what ANSYS will do by default, but you are of course free to change these. Okay. Right.
Question, is that 9-11% or 90?
90 and 110%. Yeah. Mhm. Yeah. And so I'd say that the you know, and this is my own personal commentary. So that, you know, from my own experience with optimization and other contexts, you know, a 10% difference up and below is pretty conservative. And so you're not really going to be doing that much of an exploration of the design space there. But I think that's good for default parameter because, you know, you don't want to kind of explore way too much. And so most of the time, if you kind of know what you're doing, you're going to expand this range. And so, you know, if this were me, maybe I would make the lower bound something like 15, and I make the upper bound maybe like 25, right? And so that's just for me. But you know, of course it depends on your application, and it depends on, you know, what your actual constraints are for your design. But you know, the defaults that ANSYS will give you is fairly conservative, but you know, I think that's good for you know, especially for people trying it for the first time. Okay. All right. Any questions on this? All right, and so now that we've established the input parameters, now that we've established what the outputs are, and we've put uppers and lower bounds on the design variables, we are ready to start the optimization. And so you know, we're not actually going to be doing it right now because you know, it would take way too much time, and you know, it's impossible to do by hand. But I can at least show you what to expect from ANSYS, and I can tell you what ANSYS is doing underneath the hood. Okay. Okay. All right. And so the way the optimization project process is going to work is that ANSYS is going to run several simulations with different parameters from your design variable space. Okay. Okay. Right. And so as a user, you know, what you're going to see is that ANSYS is just going to be thinking a lot, right? And so underneath the hood, it's actually running a lot of evaluations. Okay. And so just to kind of have a sense, you know, let's come up with just some upper and lower bounds for each of the parameters. And so for the length, you know, let's say that we're searching in a space has a lower bound of 15 meters. To an upper bound of 25 meters. Okay. For H is going to be the height of our cross section, and so let's say that this has a bounds of, let's say 10 centimeters to, let's say 15 centimeters. Okay. And the width, let's say that we have a lower bound of 20 centimeters to an upper bound of 30 centimeters. Okay. All right. And so with those in mind, the way that ANSYS is going to present the results to you is in a table format. Okay. And so the first three columns, or the first four columns, I should say, is going to be the trial number. Okay. And then it's going to show you what parameters it used for that trial. And so let's say that we started with the initial design. And so the initial design, let's say our default value was 20 meters. Okay. For our H, let's say that this is 12.5 centimeters. Okay. And then for a W, let's say the default value was 25 centimeters. Okay. Okay. And then from there, it's going to show you, what it's going to run the simulation with those variables. Okay. And so once it ran the simulation, it's going to tell you, what the stress was at this location. Okay. And so let's say that the stress is going to be sigma 1. Okay. And the cost will be $1. Okay. And so let's just say that we ran the simulation. Okay. All right. And so that's the first iteration of the optimization. Okay. And so the first iteration is always going to be the initial design. Okay. From there, ANSYS is going to modify these input variables, and it's going to look like it's doing it in kind of a random fashion. So let's say that it's changing the length. So let's say it changed to 20.87. Let's say it changed the height to 10.64, and the width, let's say it changed to 28.34. Okay. Right. And so it's going to look like it's something kind of random. And so it's not supposed to be kind of a discrete variable. Okay. And then from that, it's going to run the simulation, and it's going to get different values for the stress and different values for the cost. Okay. All right. And so that's iteration 2. Okay. And so after iteration 2, it's going to change the variables up again. So let's say that we change this. So now let's say that this is 24.1. For the H, let's say that this is now 14.67. And then for the width, let's say that this is changed to 22.8. Right. So there's no rhyme or reason to how I'm choosing these variables. These are just kind of random. So okay. Right. And so, for each time that it chooses a different design variable set, it's going to run a simulation. So each line in this table is a separate finite element simulation with a very slightly different geometry. Okay. And so it's going to repeat this, lots and lots and lots of times. And so, I only had room for 5 on this table here, but in reality, if you run your optimization, this could be anywhere between like 50 and like maybe a couple hundred. And so the one that I ran over lunch when I was out at lunch today, that one took about, I want to say 167 simulations in order to complete the optimization. But that's not the one we're going to do in class. And so that I was kind of pushing it a little bit for that one. And so I'm going to do one for the class that's a little bit cheaper, just so we don't spend most of the lecture just kind of sitting here and waiting. And so. But it can get really expensive. And so this is going to go on and on and on and on. All right. Any questions on this so far? Okay. All right. And so the optimization will continue. Okay. And so while the optimization is continuing, you can monitor, what the values of your outputs are and what the values of your input parameters are. Okay. Okay. And so ANSYS will actually show you a bunch of these little little line graphs. Okay. Actually, no, I don't want to say time. Okay. So on the x-axis here, we have the design points. Okay. Oh, by the way, so the each unique set of each of your input parameters, that's known as a design point. Okay. Okay. And so each unique, in this case, each unique set of L, H, and W, that's considered one design point. Okay. And so each row in the table is one design point. Okay. Okay. All right. And so to monitor your progress, it's going to look something like this, right? And so let's say that, we have a graph here that represents stress. Okay. And so what you should see at first is that, you should see it kind of change kind of rapidly, right? Okay. And then what you'll see is that it hopefully reaches a point, where it's going to steady out. Right? So a curve like this is not that uncommon. Okay. And so you can see that there's kind of two distinct phases here to the optimization. Okay. And so in this first phase, this is what I like to call the exploration phase. Okay. Right. And so in the exploration phase, the way that you kind of think of it as ANSYS is taking, saying that, I have these three design variables, I have their uppers and lower bounds. Let's just try random shit. And then let's see, what the values of the output variables are going to be, as we kind of semi-randomly choose the input parameters. Okay. And so you're going to see that that your outputs are going to change pretty wildly in value very rapidly. Okay, because it's kind of doing I call it like an exploration of the design space. Okay. And so after the exploration phase is done, it then enters a phase where the value kind of stabilizes at hopefully a small value. Okay. And so this phase is what I like to call like fine tuning. Okay. Right. And so after it's done exploring and after it's done doing a bunch of random shit, then it said that parameters in these spaces, when we kind of hit the minimums of these outputs, these are parameter sets that should work well for us. And so let's explore in that space a bit more compared to the bigger overall space. Okay. Right. And so eventually you should see a graph that kind of looks like this. Okay. And so one last comment that I want to make before before we move on from this page is that the number of design points or the number of simulations that ANSYS will run will depend strongly on how many input variables that you have. And so the more input variables you have, the more simulations it's going to take to find an optimal solution. Okay. And so we have 3 here, and three is actually a little bit more on the expensive side, for all things considered. And so, this might take, maybe at least 150 or 200 simulations to converge. Okay. All right. Any questions on this? And so when an optimization completes, when ANSYS is done running all the simulations, you can have it show you, which design point or which set of input variables produce the best results. Okay. Okay. Right. Based on that best set, you can then have ANSYS automatically apply that to your design, and then you can run a simulation on that and actually produce your plots. Okay. Okay. And so you can use, and then you can run the simulation to produce like your total deformation field, your equivalent stress field, right? And so just like we've always, okay. And so on the activity, I'm going to have you do this. And so after ANSYS finds the optimal design, I want you to basically test that out and show me, what does the best stress distribution look like, or what does the best deformation distribution look like? Okay. All right. And so that's the basics of optimization. And so, now that you have that knowledge, we can go ahead and take that and run with it on Wednesday. Okay. But I did want to give you a little bit of trivia, before we go. Okay. And that's, with regards to the question of how does the optimizer actually choose the values of your of the input variables. Okay. Okay. Because visually, what you'll be seeing on ANSYS is that, they'll be changing the values of your input variables. And, it's going to look kind of random, but there actually is a method to their madness. Okay. And so the way that it does this is based on what the optimization method is, or what optimization algorithm that you choose. Okay. Okay. Right. And so, there's literally tons and tons of different optimization algorithms out there. All right. And there's kind of way too many to even talk about in even a full semester course. You can't cover all of them, just because there's so many, and some work for very niche problems, some are very general and they work for a lot of stuff. But there's all kinds of optimization algorithms under the sun. And so I had a colleague who really specialized in this stuff, and he was a really big really big expert on this. And so I know kind of the depths through which this can go. Okay. And so ANSYS will give you the option to choose an optimization method of the, that you can, that it'll use, okay? Although granted, ANSYS doesn't have that many. So it has, I want to say like 6 or 7 of different algorithms, which is a decent number, but it's, it's definitely not an exhaustive list, okay? Okay. And so, I would say most of the time, you shouldn't have to change the method because the default one should work pretty well. But, I will say that each of the methods will give you different performance. And so, if you're having trouble finding an optimal solution with one method, and so, no matter how many times you run it, then you don't get an answer that you're really satisfied with, try changing up the optimization method and see if that helps you get a better solution. Okay. Okay. And so changing the method will, sometimes give you the results that you want from your optimization. Okay. I would say this shouldn't be the first thing that you try. And so, when you're first running an optimization, just use the default method that they have available. And if it's not too difficult of an optimization problem, it should be fine. But if you're and so for the activity Wednesday, you should be fine just using the default one. But when you're out there in industry and you want to get better performance, or you're not happy with the solution you're getting, try changing up the method and seeing if that see if that helps you out. Okay. All right. Any final questions on this before we wrap it up for today? Okay, all right, and so we ended up a little bit early today, so we ended about 5 minutes early, but that's all we have to talk about for optimization. And so when we come back on Wednesday, then we'll do an activity where you can kind of practice all these things in motion. And so, hopefully this is something that it's really cool, because I think it's something that's really cool for me too. Right? All right, so have a great evening, everyone. I'll be grading your midterm projects, before the end of the week, and so you should know by then. Okay, and I'll see everyone on Wednesday for our activity. Sure.
For the safety factor, they use the Young's module as a material, or
Yeah,
yeah. If I can't find the
They are different, so they're not the same. If you can't find the yield strength, maybe try to find the yield strength of a similar material. And so I will use that. But the Young's modules and yield strength are very different.
What's the
The Young's modulus, that's a measure of how much it resists cycling. And so an object with a higher Young's modulus is going to be harder to define.
So how would you test that in terms of like material?
So if it's a material that's been used before, usually the Young's modulus is calculated, so you can go look at table and you can find or search up the material data sheet online. Usually it's usually one of the first parameters that you see there.
So would we go look up the how would you, I guess like my other question would be like how to compare like the modulus to like the same to determine how the resistant structure is.
Yeah, so you would input that in the material type. And so when we define like a new material, one of the properties that you have to define is the Young's. And so you would input it there, and then based on that, ANSYS will determine how much it deforms in response to that.
Okay, so it will be with respect to that.
Exactly. Yes.
This stuff that you can.
Thank you.
Yep.
Yeah, like, exactly, that's on, it's great for your money, it's great. Like right now.
So I don't have it in down, but depending on the for the minutes
And all that
project.
shit.
Okay.
but
Is
like,
there
once
like
you get some
pass
interviews
through
and
or
all
Sure, yeah. Let me see, let me check and see if anyone else can apply for the other question, and I'll come back. Did anyone here have any questions before I close up the Zoom call?
What's up?
Yeah. Yeah, mechanics. Right.
Okay, all right, so I'm not seeing any questions, so I'm gonna go ahead and close up the Zoom call, so I'll see everyone on Wednesday.